Pressure. Pressure is equal to the force applied divided by the area over which the force acts. So we can write P equals F over A. If the force is measured in newtons and the area in square meters, pressure will be in newtons per square meter. The newton per square meter is called the pascal. The pascal is a very small unit, and atmospheric pressure is around 100,000 pascals. Let's look at this in a very simple case. Here we have a block of weight 500 newtons. The dimensions of the block are 5 meters by 1 meter by 2 meters. So at the moment, the way the block is resting, its pressure will be force divided by area. The force is the weight of the block at 500 newtons. The area of this bottom face is 5 meters by 2 meters, giving a pressure of 50 pascals. If we rest the block on this face, now its pressure is still force over area, the force is still 500 newtons, the area is now 1 meter by 5 meters, so it now exerts a pressure on the ground of 100 pascals. The area going from this face to this face is halved, and so the pressure has doubled. If we now upend the block like this, its pressure is now still the 500 newtons, but now the area is 1 meter by 2 meters, giving a pressure of 250 pascals. So you see, as the area reduces, the pressure increases. A pressure difference causes fluids, that's liquids or gases, to move. Here we've got a pipeline containing a fluid, and we've got the pressure A at this point, pressure B at this point, and if pressure A is greater than pressure B, the fluid will move to the right, like this. Now let's look at how pressure varies with depth in a liquid. Here we have a container of cross-sectional area A, and I'm going to find the pressure at this point, a depth h below the surface. Well, as usual, pressure is equal to force divided by area, but the force now is the weight of the liquid above this point, and so the force is equal to the mass times the gravitational field strength of that liquid. But the mass is equal to the density times the volume, so we find that the weight or force is equal to density times volume times gravitational field strength. The volume of this liquid is equal to the depth multiplied by the area, so we get that the force is equal to h rho a g. So the pressure is equal to h rho a g divided by the area over which it acts, and the areas cancel to give pressure at a depth h is equal to h multiplied by the density of the liquid multiplied by the gravitational field strength. So for an incompressible fluid, that is a liquid, pressure is directly proportional to the depth. The situation is more complicated in a gas, as the density will also increase with depth as the pressure increases. Water has a density of 1,000 kilograms per cubic meter, so to find the pressure caused by a 10-meter depth of water, we can use the equation pressure is equal to depth multiplied by density multiplied by gravitational field strength. Putting the numbers in, this gives a pressure at 10 meters depth of about 98,100 pascals. This is close to atmospheric pressure, and so just 10 meters below the water surface you experience twice the pressure that you experience on the surface. This is because the atmospheric pressure will add on to the pressure due to the water, giving a total pressure at the depth of 10 meters of around 200,000 pascals. The extreme pressures found even further down can cause problems for divers and for submarine designers. A simple way of demonstrating the increase of pressure with depth is to have a container of water like this, with a hole at the bottom, in the middle and near the top. The water at the bottom spurts out under a high pressure, in the middle the pressure is lower, and at the top the pressure is even lower. Here we have the cross-section of a ship floating in the water, and the pressure will act against the surfaces of the ship like this, with the arrows increasing representing the increasing pressure as we go down. The horizontal components of the forces due to the pressure will act against each other. For example, the horizontal component of this force acting in this direction will be cancelled out by the horizontal component of this force acting in this direction. This will cause a crushing force on the hull. The hull will have to be designed to withstand this. However, the vertical components will produce the upthrust which keeps the ship afloat. So the vertical component of this force will be acting in this direction, pushing the ship up.